The Cascadia subduction zone is currently operating under a profound mechanical paradox. Across a 1,000-kilometer expanse of the Pacific Northwest maritime border, the deepest structural layers of the most dangerous fault system in North America are in motion, yet the surface remains completely motionless. This is a silent displacement, an entire tectonic margin executing a massive transfer of kinetic energy without producing a single vibration felt by the human populations residing directly above it. The rules of standard macroseismic observation are suspended here. For 326 years, this boundary has accumulated elastic strain, and the data captured over a single 24-hour window reveals that the engine responsible for driving this system toward its ultimate mechanical limit is fully engaged from end to end. The scale of this geophysical deficit is precisely logged by automated monitoring networks. Last night, the Pacific Northwest Seismic Network registered 307 distinct tremor signals along the fault interface. Taken in isolation, 307 faint acoustic signals do not deviate from background statistical baselines. The anomaly lies in their spatial distribution. Rather than clustering within a localized segment, as is typical for routine strain releases, these signals illuminated the entire fault geometry simultaneously, stretching from the northern terminus near Vancouver Island down to the southern boundary offshore Northern California. Every intermediate segment activated in unison. Compounding this margin-wide activation, an automated station recorded a localized magnitude 2.6 earthquake at the southern end of the zone, localized at a depth of 16 miles, roughly 26 kilometers beneath the seafloor. While a magnitude 2.6 event on an ordinary crustal fault is seismically negligible, its depth changes its meaning completely. At 26 kilometers down, this event occurred far beneath shallow, localized surface structures like the Little Salmon Fault Zone. It occurred directly on the plate interface, precisely where the oceanic plate grinds beneath the overriding continental crust. This deep boundary marks the exact threshold where a critical structural division governs the fate of the Pacific Northwest. The upper segment of this fault system is cold, rigid, and completely locked, functioning as a massive mechanical spring that is wound tighter with each passing year. This locked zone is where the catastrophic magnitude 9.0 earthquake of the year 1700 originated, and it is where the next major rupture will initiate. Directly beneath this rigid barrier lies the source of last night's data, a hotter, high-pressure regime where the rock no longer snaps, but undergoes continuous, stable creep. This lower zone is whispering through a faint, uninterrupted seismic hum known as tremor, a signal so weak it can only be detected by specialized, hypersensitive array instruments. The fundamental mechanical reality is clear. The zone producing the tremor is not the zone that generates the disaster. However, they are inextricably bound as parts of a single continuous machine. Last night, the whispering zone achieved absolute spatial saturation along its entire length, signaling that the lower fault has entered a phase of accelerated slip, forcing an immediate re-evaluation of the structural load currently pressing against the locked locks above. This margin-wide surge in tremor is the visible signature of a process known as episodic tremor and slip. Over the last 25 years of geodynamics research, this mechanism has emerged as a fundamental component of the earthquake cycle. On a cyclical schedule that varies by region, the deep, ductile interface of the Cascadia Fault slips silently over a period of 1 to 2 weeks. This slow slip event releases an amount of energy equivalent to a major, high-magnitude earthquake. But because the kinetic release is distributed across hundreds of hours instead of a few violent seconds, the ground surface experiences zero acceleration. The faint hum of tremor maps the exact geographic boundaries where this slow slip occurs. These events adhere to distinct regional rhythms along the fault geometry, recurring every 14 months in northern Washington and southern Vancouver Island, stretching to 22 months in central Oregon, and activating on a much tighter, more frequent clock at the southern end of the system. The immediate systemic danger of episodic tremor and slip lies in the direction of its energy transfer. When the deep zone slips silently, it does not dissipate the tectonic strain accumulating within the Earth. Instead, it pushes. Every millimeter of displacement along the deep, creeping interface acts like a slow, unyielding hand compressing an already loaded spring, transferring the displaced load directly onto the cold, rigid, locked zone above it. This is the peer-reviewed, mainstream reality of the fault machinery. Each episode of deep slip inches the shallow, locked patch closer to its absolute structural failure limit. Consequently, during a major episodic tremor and slip event, the mathematical probability of triggering a megathrust earthquake ticks upward above baseline background levels. While the vast majority of these deep slip events conclude without a surface rupture, regional agencies have historically issued quiet, low-key technical advisories to acknowledge that the fault system has temporarily entered a more heavily loaded state. This loading process is operating against a tight historical countdown at the southern end of the margin. The Cascadia fault does not behave uniformly across its 1,000-kilometer length. The southern segment, running offshore southern Oregon and northern California, has a significantly shorter recurrence interval than the rest of the system. While the full margin ruptures from end to end roughly once every 500 years on average, the southern third frequently breaks independently on its own shorter cycle of 200 to 300 years. The arithmetic of this segment is unforgiving. It has been 326 years since the last major rupture in the year 1700. The very segment that exhibited the freshest seismic activity and the deep magnitude 2.6 stress quake last night is the exact same segment that has extended furthest past its own historical average. The localized magnitude 2.6 event acts as a critical structural indicator. Geophysicists classify this type of localized failure as a stress quake, a small rupture that occurs not because the primary locked fault is failing, but because the surrounding deep rock is being twisted, stretched, and squeezed by the slow slip movement occurring adjacent to it. It is a symptom of rapid load redistribution within the segment with the tightest recurrence clock on the entire continent. This data completely dismantles the superficial narrative that a small earthquake acts as a safety valve to release pressure and prevent a larger disaster. A small quake at 26 kilometers depth does not relieve the strain of the system. It confirms that the deep engine is actively loading the locked zone toward its breaking point, driving the southern segment closer to a threshold where the rock can no longer sustain the structural load. To fully comprehend the catastrophic potential of the structural load currently accumulating within the system, we must examine the exact scale of the baseline event written into the geologic record. On the evening of January 26, 1700, at approximately 9 o'clock local time, the entire Cascadia subduction zone experienced a simultaneous, end-to-end structural failure. The magnitude of this megathrust rupture is estimated between 8.7 and 9.2, with the primary empirical models placing it at 9.0. The crustal displacement tore through roughly 1,000 to 1,100 kilometers of the fault boundary. In a matter of minutes, the oceanic and continental plates violently lurched past each other by an average of 19 meters, or approximately 62 feet. For physical scale, this represents a sudden tectonic displacement taller than a 5-story building, executed across the entire length of the Pacific Northwest coastline. A structural failure of this magnitude triggers two catastrophic macro-environmental consequences. First, it generates violent ground accelerations that endure for several consecutive minutes rather than seconds. a duration sufficient to induce catastrophic failure in unreinforced engineering structures across an immense geographical footprint. Second, because the fault trace lies offshore beneath the ocean floor, this massive vertical displacement abruptly shoves the overlying seabed upward, transferring immense kinetic energy into the water column and launching a destructive trans-oceanic tsunami. In the year 1700, this displacement wave initiated an elegant chain of physical cause and effect that allowed modern geophysicists to pin down the precise calendar date of a disaster that occurred long before European or American instrumental records existed on this continent. The resulting tsunami crossed the open expanse of the Pacific Ocean, arriving at the coast of Honshu, Japan, approximately 9 to 10 hours after the initial fault rupture. Local administrative and temple officials maintained rigorous chronological written records, logging a highly destructive wave that inundated coastal villages with absolutely no local earthquake to account for the disturbance. For 3 centuries, this phenomenon was documented in Japanese history as an orphan tsunami, a massive flood arriving out of a calm sea without an apparent parent event. The physical parent was definitively identified 300 years later on the opposite side of the ocean, where the evidence of sudden co-seismic subsidence was permanently recorded by the landscape itself. When the fault ruptured in 1700, the immediate subsidence of the coastline caused marine saltwater to abruptly inundate low-lying coastal forests, drowning entire stands of red cedar and Sitka spruce where they stood. These dead ecosystems left behind gray, skeletal trunks rooted in modern tidal marshes, structures geologists now classify as ghost forests. By utilizing high-precision dendrochronology to count the growth rings of these drowned trees, matching their final terminal year of life against the written Japanese imperial wave logs, and cross-checking both records against the oral histories preserved by First Nations tribes from Vancouver Island to Northern California, science reconstructed the exact moment of structural collapse. January 26, 1700, at 9 in the evening. This paleoseismic record extends back 6,500 years, revealing a history of 19 such megathrust events. The hard data dictates that full margin failures recur on average every 500 years, while the southern segment runs on its own independent higher frequency cycle of 200 to 300 years. Having passed both the southern recurrence clock and entering the critical window for a full rupture, the current margin-wide tremor data confirms the engine of loading is actively driving the system toward a repeat of this documented historic baseline. The empirical reality of this 500-year recurrence cycle forces researchers to establish precise mathematical probabilities for near-term failure. Over the next 50 years, the statistical probability of a full margin magnitude 9.0 rupture is calculated at roughly 10 to 15%. However, the probability of a partial rupture confined to the southern segment, generating a magnitude 8.0 or greater event, is significantly higher, commonly cited at 30% and scaling up to 37% when all southern tectonic scenarios are integrated. These metrics represent a serious, non-trivial hazard profile, equating to a 1 in 10 minimum chance of the single largest natural disaster in the modern history of the continent occurring within the lifespan of an individual alive today. Yet, these figures do not establish a specific day, month, or year of failure. This discrepancy between the physical certainty of an active, loaded fault system and the absolute inability to forecast the exact moment of structural collapse defines the permanent baseline condition of the Pacific Northwest dot. While the public map hosted by the Pacific Northwest Seismic Network remains entirely open, allowing anyone to verify the 307 tremor points in real time, the data does not provide an early warning countdown. Instead, it confirms that the structural loading process is running across the full length of the system. This baseline complexity is further compounded at the far northern boundary of the margin, off the coast of Vancouver Island, where advanced seismic imaging has revealed a deep structural fragmentation within the subducting oceanic crust itself. The subducting slab is not descending as a single, uniform sheet. Instead, the small explorer plate at the northern tip of the system is actively tearing apart piece by piece, resembling a train slowly derailing as it enters the mantle. The dimensions of this internal rupture are severe. A subterranean crack penetrates approximately 35 kilometers horizontally through the explorer plate and plunges 5 kilometers straight down through solid oceanic rock. This northern structural tear is highly active, having generated multiple earthquakes of magnitude 6.0 and greater within the past 2 decades. Geodynamic projections indicate that the explorer plate will completely detach from the primary system within roughly 1 million years, an event that will ultimately shorten the active Cascadia subduction zone by approximately 75 kilometers, or 1/12 of its current total length. However, this macrostructural fragmentation does not alter the near-term seismic hazard for the rest of the region. The tearing is isolated to the far northern extreme and does not drain, alleviate, or impact the immense elastic strain sitting along the primary locked length of the fault offshore Oregon, Washington, and Northern California. The current system state, therefore, presents 2 distinct competing scenarios. On one side is the full margin magnitude 9.0 rupture, a direct replication of the 1700 event, which would cause several minutes of violent ground motion, followed by a destructive tsunami striking the coastline in as little as 15 to 20 minutes. On the other side is the more statistically probable scenario, a partial rupture of the southern third of the fault. While a southern magnitude 8.0 event would remain a localized catastrophe, producing severe shaking and coastal inundation along southern Oregon and northern California, it would not activate the full end-to-end system. The immediate analytical question is whether the recent margin-wide flare-up will sustain itself as a prolonged episodic tremor and slip event, further accumulating load on the critical southern segment where the historical clock is furthest past its average, or quietly fade back to background baselines. The mechanical clock has been running for 326 years without interruption, and the silent hum of the lower fault confirms that the tectonic engine is actively moving. The immediate trajectory of this system over the coming days depends entirely on how the deep fault interface handles the current redistribution of stress. Geophysicists are closely monitoring the automated public tremor map to determine whether this margin-wide activation marks the definitive onset of a prolonged, full-scale episodic tremor and slip event, or a transient fluctuation. If a major slip episode is underway, the silent tracking instruments will register a continuous, dense propagation of tremor points, filling in the southern segment over the next 1 to 2 weeks. This sustained activity would confirm that a massive volume of deep rock is executing a slow, silent displacement and systematically shifting its structural load directly onto the cold, rigid mechanical locks above it. Alternatively, the energy may dissipate, allowing the entire margin to quietly subside back to its baseline background level, an outcome that is equally common within the recorded history of the fault's behavior. Simultaneously, the isolated magnitude 2.6 earthquake at the southern boundary remains a critical point of tracking. The fundamental question is whether this event will remain a solitary stress quake, representing a minor, localized failure in a zone undergoing ductile creep, or if it will evolve into the leading edge of a dense cluster of small, deep crustal ruptures. A growing sequence of small stress quakes at a depth of 26 kilometers would provide empirical confirmation that the slow slip process is actively transferring a highly significant volume of structural load into the specific segment that possesses the shortest recurrence interval on the continent. A single, quiet tremor that never repeats would indicate that the system is merely executing a routine mechanical adjustment, The physical system itself will deliver the definitive answer through the open seismic networks, leaving no room for privileged interpretations, inside information, or early proprietary warnings. Every observer, from research institutions to the public, is viewing the exact same data stream at the exact same moment. This absolute parity of information underscores the most severe boundary of the Cascadia fault system: the absolute absence of a predictive warning before a catastrophic rupture occurs. This is the unyielding physical limit that both scientists and the human populations on the surface must accept. The deep tremor remains completely silent to all human senses, and the underlying slow slip cannot be calculated into a predictive calendar forecast. The historical record confirms that when this subduction zone reaches its absolute mechanical limit, it gives no felt indication prior to failure. In the year 1700, the only immediate record of the sudden tectonic collapse on the opposite side of the ocean was a sudden, unexplained wave arriving on a calm day, leaving a mystery that required 3 centuries of advanced cross-disciplinary forensics to solve. Consequently, the standard emergency advisory issued to populations within the Pacific Northwest to secure autonomous water supplies, physical provisions, and to map immediate evacuation routes outside defined tsunami inundation zones is completely independent of yesterday's specific tremor count. These protocols are dictated by the permanent, immutable reality of a massive tectonic subduction zone that will inevitably fail again. The recent margin-wide activation did not initiate this mechanical countdown. It simply served as an unambiguous, real-time indicator that the loading process is active, continuous, and running without interruption. The mechanical clock has been ticking for 326 years, and the silent engine driving the system toward its structural limit has not stopped.